4.5 Forces between two parallel current carrying conductors. Learning outcomes. A. Explain magnetic force per unit length of two parallel current carrying conductors. And B. Derive and use magnetic force per unit length F per L equals to mu naught I1 I2 divided by 2 pi D. Consider two identical straight conductors 1 and 2 with length L carrying currents I1 and I2 in the same direction with separation distance of D. Around conductor 1 we have B1 and around conductor 2 we have B2. To determine direction B magnetic field, we use right hand grid rule. So direction term is direction for current. Okay, so I1 here, direction I1 outward. So you can determine direction B1 around conductor 1. So direction B1 here anti-clockwise. And around conductor 2, we have B2. We apply right hand grid rule. So direction current I2 outward. So you can determine direction B2 around conductor 2 here anti-clockwise. Direction B1 at conductor 2, okay, at point conductor 2, B1 here is into the page. So to determine direction force, we use right hand pump. Direction for thumb here is direction current. Okay, non-direction finger here is direction for magnetic field. And palm here direction for force. So we apply here direction I2 outward and direction B1 into the page. So you can determine direction force. So you get here direction force towards conductor 1 or to the left. So we can label here F21. F21 is force on conductor 2 due to conductor 1 and direction to the left or towards conductor 1. For B2, around conductor 2, at conductor 1, at point conductor 1, so direction B2 here we get out of the page. So we can label B2 here out of the page. When we apply right hand palm, direction current I1 outward, direction B2 here out of the page. So you can determine direction force. So you get direction force towards conductor 2 or to the right. So you can label here F12. F12 is a force on conductor 1 due to conductor 2 and direction to the right or towards conductor 2. So it means that two conductors attract to each other. We call it attractive force. So the current are in the same direction. Two conductors attract each other. The magnitude of the magnetic flux density B1 at any point on conductor 2 due to the current in conductor 1 is given by B1 equals to mu naught I1 divided by 2 pi d, and direction for B1 into the pitch. Then the magnitude of the magnetic flux density B2 at any point on conductor 1 due to the current in conductor 2 is given by P2 equals to mu naught I2 divided by 2 pi d, and direction B2 here out of the pitch. So to determine direction of B1 and B2, we use right hand grid rule. And from using right hand grid rule, we can determine direction B1 into the page and direction for B2 out of the page. And to determine for direction of force F12 and F21, we use right hand pump. We use right hand pump, so you can determine direction F12 and F21. So force on conductor 1 due to conductor 2, F12 directed to right, and force on conductor 2 due to conductor 1, F21 directed to left. So two conductors attract to each other. We call it attractive force. To determine the magnitude of force, we use equation F equals to BRL sine theta. So magnitude F21 equals to B1 I2 L sine theta. So theta here equals to 90 degree. Theta is angle between B and L. So angle theta 90 degree. And B1, we use equation B1 equals to mu naught I1 divided by 2 pi d. So we substitute into equation F21 here. So you get F21 equals to mu naught I1 divided by 2 pi d times I2 L sine 90 degree. So sine 90 degree equals to 1. So you get magnitude F21 equals to mu naught I1 divided by 2 pi d times I2 L. And direction for F21 to the left or towards conductor 1. Then to determine magnitude of F12, so magnitude F12 equals to B2 I1 L sine theta. So theta also 90 degree between B2 and L. And then the magnitude B2, we use equation B2 equals to mu naught I2 divided by 2 pi d. So we substitute into this equation. So you get F12 equals to mu naught I2 divided by 2 pi d times I1 L sine 90 degree. So sine 90 degree equals to 1. So you can determine magnitude F12 equals to mu naught I2 divided by 2 pi d times I1 L. And direction F12 to the right or towards conductor 2. So it means that here magnitude F12 is equal to magnitude F21. So let's say equals to F. So you can write magnitude F12 equals to F21 equals to F equals to mu naught I1 I2 L divided by 2 pi D. Okay. And force between F21 and F12 here, we call it attractive force. If the direction of current in conductor 2 is changed to upside down as shown below, so to determine direction magnetic flux density B1 and B2, we can use right hand grid rule. To determine direction B1, direction current I1 is outward, so it means that direction thumb outward. So you can determine direction B1. So direction B1 here is anti-clockwise. So direction B1 at point P is into the page. And then to determine direction B2 around conductor 2, we use right hand grid rule, but direction I2 is downward, so it means that direction thumb downward. So you can determine direction B2 clockwise. And then direction B2 at point Q is into the page. And then to determine direction force F12 and F21, so we can apply palm right hand. So we can apply palm right hand at point Q. Direction current I1 is upward and direction B2 into the page. So you can determine direction force F21 here to the left. So we can label it F21. Then at point P, direction current at point P, I2 is downward. So it means that direction thumb downward. And direction B1 is into the page. So you can determine direction force F12. So direction force F12 is to the right. And we can label it F12. So magnitude F12 is equals to magnitude F21 equals to F equals to mu naught I1 I2 L divided by 2 pi D. So it means that if the current are in the opposite direction, two conductors are repel each other. So we call it repulsive force. So conclusion here, if the current are in the same direction, two conductors attract each other. But if the current are in the opposite direction, two conductors repel each other. So magnitude F12 equals to magnitude F21 equals to F equals to mu naught I1 I2 L divided by 2 pi D. So we rearrange this equation to determine F per L. So F per L equals to mu naught I1 I2 divided by 2 pi D. If I1 equals to I2 equals to 1 ampere, and distance between conductor 1 and conductor 2, D, equals to 1 meter. So you can determine F per L. So you get F per L equals to 2 times 10 to the power of negative 7 Newton per meter. So F per L equals to 2 times 10 to the power of negative 7 Newton per meter. We call it definition of 1 ampere. So 1 ampere is that constant current which, if maintained in two straight parallel conductors of infinite length of negligible circular cross-section and placed 1 meter apart in vacuum, would produce between these conductors a force equals to 2 times 10 to the power of negative 7 Newton per meter. So 1 ampere is the flow of 1 coulomb per second.
4.6 Torque on a coil. The outcome, use torque tau equals to NIA cross B, where N equals to number of turns. Torque is a cross product, so it means that torque is a vector. So torque have a magnitude and direction. To determine the magnitude of torque, we use torque equals to NIAB sine theta. And theta is angle between vector A and vector B. Vector A here is a cross-sectional area, and vector B is a magnetic field. And to determine the torque, we can use right hand pump. Okay, here is rectangular loop. P, Q, R, and S. If current I, okay, we have side 1, side 2, side 3, and side 4. And here is B, magnetic field. So direction magnetic field here from left to right. This diagram here is top view. The top view. So we consider a rectangular loop PQRS with length A, and here is length A, and width here B is provided so that it can be rotated about a vertical axis. Vertical axis, here is vertical axis, which is at right angle to a uniform magnetic field B. Okay, when a steady current I passes around the coil, a magnetic force acts on each side of the coil. But there is no magnetic forces act on side 1, PQ, and side 3 here, SR, because these wires are parallel to the field, to the magnetic field. Now we consider to side 2. Here is side 2. Okay, we use right hand pump to determine direction force at side 2 here. The direction B from left to right. So here is direction field B. Okay, from left to right. And current here, side 2 here, current is downward. So it means that your thumb here downward. Okay, show the direction downward here. So direction force at pump here is out from the pitch. So direction force out of the pitch. Then side 4, we use right hand. Okay, then here is direction field, magnetic field from left to right. And current, direction current here is upward. So it means that your thumb, okay, direction here is upward. So it means that your pump here, direction here is direction force is into the pitch. So direction force into the pitch. So it means that force F2 out of the pitch and direction F4 here into the pitch. So in opposite direction. Okay, so the two magnetic forces on side 2, PS and 4, QR, okay, each of length A, okay, are equal and opposite and have the value force F. So it means that magnitude F2 equals to magnitude F4 equals to F equals to BIL. And L here equals to A. So you get F equals to BIA. Here is side view. Diagram here is side view. So meaning that here dot here is direction of current out of the page. And here point 4 here cross. It means that direction current into the page. Okay, one for F2, direction F2 upward and direction F4 downward. So it means that the system can rotate in clockwise. Okay, rotate in clockwise. Okay, so the forces excited a torque that tends to rotate the coil clockwise. Okay, so you can rotate like this. Here is F2 and here is F4. So the system rotate clockwise. So how to determine the magnitude of this torque? Okay, so the magnitude of this torque for each side is torque equals to Fd. So refer to this diagram. Here is F2 and here is axis rotation point O. So it means that here is R. Okay, so torque equals to R cross F. So angle is between R and F. So here is action line for F2. So it means that here is angle theta. If you use FD, so the angle between F and D here 90 degrees. So here is F2. So it means that this one is D. Okay, from axis rotation. So this one is D. So it means that here is half B, D per 2. So here is equal to B2 sine theta. Okay, B2 sine theta. So torque equals to FD. So it means that torque here equals to F2 B2 sine theta. Plus, okay, plus here force F4, okay, and here is D, and here is axis rotation, and here is angle theta. So you get F4 times B per 2 sine theta. Okay, and then F2 equals to BIA times B2 sine theta, so plus F4 BIA, okay, times B2 sine theta. So you get BIAB sine theta. Okay, so A times B, refer to diagram. So A times B equals to area, rectangular area. So you can, so the magnitude tau, torque here equals to BIA sine theta. Okay, if we have a number of turns, Okay, so you times N here. So you can write torque also equals to NBI A sine theta. So N here is number of turns. Okay, and theta here, sine theta, theta here is angle between V and the normal to plane of the coil. A. Explain briefly the working principles of a moving coil galvanometer. A moving coil galvanometer. This is a structure of a moving coil galvanometer. Okay, so current flow in the coil, magnetic force exerted on the coil, produce torque in the coil, and coil rotates, pointer deflects. So the coil stop rotating when torque F equals to torque spring. So the deflection of pointer shows the value of current here. So a moving coil galvanometer is the main component in an analog meters for measuring current and voltage. It consists of a magnet. Here we have a magnet. Okay, we have a coil of wire. We have coil of wire here. We have a spring. Okay, here is spring. Up here spring. We have a pointer. Okay, it's pointer. And a calibrate scale. Here is a scale. So the coil of wire contains many turns. Okay, and is wrapped around a soft iron cylinder. The coil of wire contains many turns and is wrapped around a soft iron cylinder. The coil is provided in a radial magnetic field so that no matter what position it turns, the plane of the coil is always parallel to the magnetic field. So the basic operation of the galvanometer uses the fact that a torque acts on a current loop in the presence of a magnetic field. When there is a current in the coil, so the coil rotates, okay, in response to the torque. Tau equals to NIAB applied by the magnet. This causes the pointer attached to the coil to move in relation to the scale. So the torque experienced by the coil is proportional to the current in it. The larger the current, the greater the torque, and the more the coil rotates before the spring tightens enough to stop the rotation. Hence, the deflection of pointer attached to the coil is proportional to the current. So the coil stops rotating when the torque is balanced by the restoring torque of the spring. So it means that torque due to magnetic force, torque F, equals to restoring torque, torque S, torque spring. So NABI equals to K theta. So it means that I, current, equals to K theta divided by NAB, where K here is the stiffness constant of the spring or torsional constant, and torque is rotating angle of the coil in unit radian. From this equation, the current I can be calculated by measuring the angle theta. This working This working principle of a moving coil galvanometer also used in voltmeter. We call it multiplier, ammeter, shunt, ohmmeter, and multimeter. 4.7 Application of motion of charged particle. The new outcome A. Explain the motion of a moving charged particle in magnetic field and electric field for V, B, and E perpendicular to each other. And B. Use velocity V equals to E per B in a velocity selector. Okay, consider a charged particle, positive Q, move with a velocity V here. Okay, in combined electric field and magnetic field. Then the electric field and magnetic fields are perpendicular. Okay, cross here is direction for B magnetic field. It means that direction magnetic field here is into the page. And direction for E electric field here, we have here plate positive and here is plate negative. So it means that direction E electric field from positive plate to negative plate. So it means that direction E downward. Okay, direction E downward. So the particle experience no resultant force F0. So it means that particle move in a straight line here. So how to determine FE, direction FE. How to determine direction FE? So direction FE is same direction with E if test charge is positive. So here is our test charge is positive, so it means that direction E is same direction with F. Okay, so it means that direction FE downward. Okay, direction FE downward. And to determine direction of FB, we use right hand palm, direction B into the page, direction V is direction thumb to the right. So you get thumb, so you get direction palm here is upward. So it means that direction FB is upward. Okay, so from this diagram, so you can determine V. So it means that FB equals to FE. FE equals to FB, and FE equals to QE. FB equals to BQV sine theta. Theta here is angle between B and V. So between B and V here is 90 degrees. So it means that theta is 90 degrees. Sine 90 degree equals to 1. So you get FB equals to BQB. So we can cancel Q, charge Q here. So you get V equals to E divided by B. E is electric field and B is magnetic field. So the particle will continue to move in the same direction, straight line with the same speed, because the electrostatic force downward balance with the magnetic force upward. So V here in a straight line. A mass spectrometer, we have 4 stages here. Stage 1 is ionization. This one is stage 1, ionization. And stage 2, here we call it acceleration. And stage 2 also we call it velocity selector, where both E and B are applied. We have E and B here. Okay, so you get FE equals to FB. So it means that QE equals to BQV. So you get V, speed or velocity ion here equals to E per B. Okay, so ions all have same kinetic energy, which speed or velocity E per B. And stage 3 here is stage 3 deflection. Okay, so in stage 3 we have B only, magnetic field. So dot here, it means that direction B out of the page. Okay, out of the page. And stage 4 here, okay, we call it detection. Okay, photographic plate or other detector here. So in stage 3, we have only B, magnetic field, okay, and ion here move in a circle, in circular motion, semicircular motion. So net force for circular motion equals to Fc, so Fb equals to Fc. Okay, Fb equals to Fc, Fb equals to BQV, and Fc equals to mv squared over r. Okay, so you get Q per m equals to V divided by Br. And B here is magnetic field, so B prime, we use B prime, so we mean that magnetic field is stage 3. Stage 2, here we also have B magnetic field. Stage 2, we use B for magnetic field, but stage 3 here we use B prime. So what happened in a mass spectrometer? Stage 1, ionization. The atom is ionized by knocking one or more electrons off to give a positive ion. This is true even for things which you would normally expect to form negative ions. Chlorine, for example, or never form ion at all. Argon, for example, mass spectrometers always work with positive ions. Stage 2, acceleration. The ions are accelerated so that they all have the same kinetic energy, same velocity selector. Okay, in velocity selector. Stage 3, deflection. The ions are then deflected by a magnetic field according to the masses. The lighter they are, the more they are deflected. So the amount of deflection also depends on the number of positive charges on the ion. In other words, on how many electrons were knocked off in the first stage. The more the ion is charged, the more it gets deflected. Stage 4, detection. The bin of ions passing through the machine is detected electrically.